This morning we're going to go through direct reading instruments and methods for gases, vapors, and aerosols. And direct reading instruments are generally read in either part per million or percent. And at this point, most of you can do those conversions pretty quickly. I was really pleased that most of you got that correct on the examination on how to do the conversion. And it's a handy conversion to know because you will see a lot of instruments that read out in percent. You can automatically translate that to part per million pretty readily and then compare them to any type of a recommendation or a regulation that you may have. And then there are some direct reading instruments for aerosols. They're not quite as commonly used and not quite as the data isn't quite as good from direct reading aerosols, but they're out there and they do have some applications as well. So the first part, I want to go through direct reading instruments, gases and vapors, and a little bit on aerosols. Now the first thing to know is what it is we're talking about we're measuring, i.e. what is a gas and what is a vapor. And there are definitions in industrial hygiene for what constitutes a gas and what constitutes a vapor, and they're really common sense definitions, but they are looking at any material that's in the gaseous state at 25 degrees Celsius and 760 millimeters of mercury. Just like our definitions last week on what standard temperature and pressure is, this is standard temperature and pressure. So basically room temperature conditions, if something is a gas, it's defined as a gas. And what's an example of that? Well, this environment that we're breathing now is about 80% nitrogen, 20% oxygen. They're all going to be in a gaseous state under the conditions of standard temperature and pressure. Hydrogen sulfide is another example of something that will be in the gaseous state under those conditions. Now, can you get liquid nitrogen and liquid oxygen? What do you have to do? Change your pressure or change your temperature. If anybody ever play with liquid nitrogen, if you get into, since I used to do a lot of science, liquid nitrogen was a standard laboratory research tool that we had on all of our hallways where we were doing research. At National Center for Toxicological Research, we had every floor had liquid nitrogen tanks, and every floor had a couple of freezers that went down to 77 degrees Celsius that you could freeze your samples in. And what was important is if you're doing work with enzymes, what you would do is take the enzymes out and you dip them in liquid nitrogen and you quick freeze them so that they would be stable if you wanted to do your experiment on them tomorrow or next week or even several months. They would be maintained in their natural state pretty much if you quick froze them in liquid nitrogen. And it was kind of fun too because if you're a grad student or a postdoc, what you do is you take your pencil and you'd stick it in there, then you drop it on the floor and it shatter into 100 different pieces because when you have liquid nitrogen, that's what'll happen. But it's about minus 70 or minus 80. I can't remember exactly what the temperature is for liquid nitrogen, but you can liquefy it, but you've got to get really cold or really pressurized. The same with oxygen. If you're going to be powering up rockets and things like that, you can use liquid oxygen, but you've got to do it pressurized or at cold temperatures. But under standard temperature and pressure, you're not going to see oxygen or nitrogen in the liquid state. So these are examples of things that are considered a gas. Now, vapor is a little bit different. With a vapor, what you have is a substance that is ordinarily a liquid or solid at standard temperature and pressure conditions, but you do see some that's in the gaseous phase. So it's a gaseous phase of a substance, ordinarily liquid or solid, at 25 degrees Celsius or 760 millimeters of mercury. I think a prime example of that is water. You've got water I see a lot of water around the class. And that's going to stay as water for the most part, but some of it is going to come in equilibrium with the atmosphere. And the more that comes in equilibrium with the atmosphere, the higher our relative humidity is going to be, which is an expression for oxygen for water that's in the vapor phase. If you take a solvent, I don't have it on this list, but it's a good one. Gasoline, and I open it up and put a can in the back of the room. Everybody here is going to smell it, and what you're smelling is the vapor. You have an equilibrium between the gaseous phase and the liquid phase, and the gaseous phase is what we'd be inhaling. So it's considered to be a vapor. And chemicals like trichloroethylene are also those that are predominantly liquids under standard temperature and pressure conditions, but you can have a gaseous phase occur. Mercury is a little different in that it's a solid under standard temperature and pressure conditions, but it can also have an equilibrium with the gaseous phase under those conditions as well. Really interesting chemical. Back when I was a kid, all of our thermometers had mercury in them, and we would always break them and play with the mercury because it beat up and you could roll it across the floor, things like that. Nowadays, if you do that, they'll bring in a hazmat team and cordon off the whole area and clean it up. But from a toxicological perspective, liquid mercury is really not that dangerous. It used to be used in medical treatment for about 400 years, where they'd have people drink it and see if it went through them quickly to test for intestinal blockage. So the liquid form is really not a huge toxicological hazard. The problem with mercury is the vapor phase, and if you have liquid phase out in the environment, it has a pretty high vapor pressure, and you will have an equilibrium with the vapor phase. And if you breathe in the vapor phase, especially over long periods of time, like if you have liquid mercury spilled on a rug and you go in there day after day after day, then you can get into some serious central nervous system problems, because the vapor phase is very toxic, especially as a chronic toxicant. So it's a really interesting metal from that perspective, but there is an equilibrium between the gaseous and the liquid phase, and the gaseous phase is particularly dangerous from a toxicological perspective. Now, direct reading instruments, the type that I want to talk about for the most part of today, are those that can give you a measurement in real time. So you go in an environment with these instruments, you'll look at a gauge, and you'll get a direct reading at that particular point in time. And we'll talk a little bit at next lecture about extractive sampling and some of the differences between that. The example that I gave you on Thursday about sampling for the pesticides DDT and chlordane, that was an extractive sampling technique. I did not get an answer right away. I had to run pumps for 8 hours and pull off sample on a filters because I had very, very low levels, send it off to a laboratory that charged me $250 a pop to analyze the sample, and then I got the data on what the concentrations were in air a week or so later. If you are dealing with really low levels of contaminants, that's the way you have to go, as an extractive sampling procedure. But in certain cases, if you have a high enough concentration or a sophisticated enough instrumentation, you can get an answer in real time. You can go in with a piece of equipment and turn it on and get an exact number on what the concentration is of that contaminant immediately. And that's what a real-time direct reading instrument will do. Now, why would you want something like this? These are real handy in emergency situations. For example, if something can blow up, if it's combustible, you want to know that right away. So a lot of your combustible gases and vapors will have direct reading instruments because of the potential hazard of an explosion. If you're getting into a confined space and you need to make sure the oxygen levels are adequate to support life, that's handy to know right away, and you want an answer of that in real time. You don't want to send off something to the lab and wait a week to get into the space. You want to know it immediately. So oxygen levels are a common usage for direct reading instruments. And then if you have something that's very, very toxic that could cause acute toxicity like lethality, something like phosgene or hydrogen sulfide, or something that can be extremely dangerous in an extremely short period of time, that's an application for a direct reading instrument. So there are some common usages for these as well. One of the people that I've been working with on a couple of projects and wrote the chapter in the Industrial Hygiene for Toxicology for Industrial Hygiene book is a retired Navy guy named Phil Smith, and he's done his career out of developing more sophisticated direct reading instruments for military applications. Because if you're a soldier and you go into an area that's been contaminated with some VX or sarin or something like that, you want to know the answer to that in real time. And a lot of the instrumentation is designed to not pick up really, really low levels. And so he's been working on coming up with detecting extremely low levels of contaminants to try to protect the soldiers. So there's a lot of applications for real-time instrumentation. Now, what different classes of direct reading instruments are out there? I've got a few listed here that are discussed in the chapter that I provided you to read. This is not an all-inclusive list. This is just a sampling of some, but it gives you a general idea of the type of principles that direct reading instruments used to operate. And I have the list here of electrochemical sensors, combustible gas instruments, solid state sensors, photoionization detectors, and flame ionization detectors. Okay, electrochemical sensors are really good at monitoring for a single gas and vapor. There's a lot of these things are available for. I have 50 plus. You can probably even find more than that. But an electrochemical sensor is a nice field instrument. It's the kind of thing you might use in a confined space for determining oxygen levels or hydrogen sulfide levels or things like that. Advantages, they're small. You can hold them in your hand. They're compact. They have low power requirements, so they can run off AA batteries or that kind of power requirement. Disadvantages are that they're somewhat promiscuous in that they'll be able to detect gases incorrectly, so there's a lot of interferences with common types of contaminants that may be present. There could be some contamination that can occur, and it could leak. And I'll show you what they look like in a second. And it's a chemical, kind of like a car battery, that can leak out, and that could cause a problem as well. What kind of gases and vapors can be determined by these things? There's a laundry list, and I have a busy slide here, but things like hydrogen sulfide, like oxygen, like phosgene can be determined in real time with this type of an instrumentation. Now, how does it work? It's actually a real simple system. It's sort of like a car battery in a sense. You've got an electrolyte, just like in your car battery. That's an electrolyte fluid that's present, and it sets up a charge by having ions go on one side or the other. So the way that the electrochemical sensors will work is you'll have a gas or vapor that comes in contact with this semi-permeable membrane. The membrane is permeable for that particular gas and vapor, so it can pass through it and get into this electrolyte, which is a liquid, again, kind of like a car battery, and it will cause ions to form of the gas or vapor you're attempting to measure. And the positive charges will go on one side, the negative charges will go on the other side. You'll set up a gradient, and once you do that, you can measure it. And so it's like measuring the current that can go through this based upon the concentration gradient. So it's a real simple system, but it's very effective for a lot of gases and vapors that you can create ions with. And again, the problems with leakage are that this can break. It's in a sealed system, but it can also break out. And if it does that, then it can leak and cause a problem, and that could be an issue. Or you could have another gas and vapor get in here and ionize as well, and so it could have cross interferences. It could measure that instead of what it is you want to measure, or it could be contaminated because this is a semi-permeable membrane. So there are some limitations with this type of system. Your gas or vapor may not be the only one to get in here. The other one could stay, interfere with what you're trying to do. So there are some potential issues with using this. But nonetheless, it's a real common type of instrumentation. Draeger makes a lot of these, or little sensors that you can put on the top. You can buy them for oxygen or hydrogen sulfide or any of those gases and vapors that I had on the list. So you can change out the sensors. As a handheld instrument, it looks like this. This is a Draeger PAC 3. Other companies make these kind of things as well. I'm just using this as an illustrative purpose. This particular one you can use to monitor up to 35 different gases and vapors. And it can use a lot of Draeger sensors. So let's see if I can get a picture here of this. This is a Draeger monitor. A couple things about this. The reason I'm showing this, you can go to these and read about them. They can tell you exactly what they can do, what their ranges are, what they can pick up. A lot of these they can pick up in percent. Some of them by part per million. They'll list that and how it's going to read out. And so they can give you some indication on how they'll use the particular unit. This one it says not to use for processed gases. But the other thing about a lot of these sites is that many of you are going to be, you've turned in your papers, you're going to start writing your articles, and part of your article is going to be a cost analysis. And maybe your paper actually used the Draeger tubes or similar equipment that I'll be talking about today. And you can go and look at these different websites from the different vendors, and there are a lot of industrial hygiene vendors. I'd recommend you do it that way rather than eBay. And sometimes they will give you a price, and sometimes they won't. Sometimes they will give you a rental price, and if that's all you can get, that's fine. The other thing is that if you want to know what the unit's going to be, you may get this down here, call for pricing. This is pretty common. And what you need to do in that case is attempt to get a price for it. You know, tell them you're working on a project and maybe you don't need an exact price, but you'd like kind of a ballpark range. And they can help you with determining about what that's going to be. And if they won't do that, then I'd be perfectly happy with the rental price if you can provide documentation. Say, I don't know what the price is, they wouldn't tell me, but I do know it's $120 a month because this is it on the website and printed out, and that's that documentation of what that is. But I would encourage you to try to contact the company and talk to them a little bit about what the price is. And if they're rude to you and tell you to jump in the lake, make a note of that and remember it because, you know, over the next couple of years you're going to be buying equipment from vendors, and people that were nice to you, you need to remember, and the people that were rude to you, you need to remember those people too. If you have a choice about who to do business with, or you don't have to do it that way. I'm just saying that if they're rude to a student, that may not be the best people that you want to do business with down the road. But a lot of this equipment does have some pricing built into it for sales commissions. It's kind of like buying a car. They're a little reluctant to let you know what their prices actually are, but they may give you a range, and that could be pretty helpful as well. But if you can't get that, go with the rental price. Okay, now there's other types of instruments that can measure more than one. They can measure a wide range of gases and vapors, and these include those that I talked about earlier, the combustible gas instruments, solid-state sensors, photoionization detectors, and flame ionization detectors. Now, the oldest ones are the combustible gas instruments, and these are the first direct reading instruments that were ever developed. They work on the process of having a Wheatstone bridge, and I'll show a picture of that in a second, but they have what they measure is thermoconductivity. If you have a Wheatstone bridge, you have two places, you have a current going through a wire, and you heat up one part of the wire and not another part of the wire. And a hot wire has more resistance than a cold wire does, and you can measure that with a Wheatstone bridge. So it's an application of burning a gas over a wire and heating up the wire, and you can measure the resistance in the circuit from that. Now, there's a couple of problems with that on the front end, and when I show you the diagram, you can get this a little bit better. But a couple of problems are both calibration and sensor deterioration. Now, we're in the process now of phasing out our incandescent light bulbs, but y'all know how those work. An incandescent light bulb has a wire that goes across the inside of the sealed bulb of your light bulb, and you flick on the wire, you flick on that power, and light comes out. And it's made by passing a current across that very thin filament wire that you have inside of your light bulb. Now, if you use a light bulb, you buy some, it'll say this is good for X number of hours, 500, 1,000 hours, or something like that. And as you use it, what you don't really realize, and if you had a sophisticated instrument, you could pick this up, but every time you turn it on, it's going to be a little bit different than the time you turned it on before, because it's going to be deteriorating over its life. And so when it's brand new, it's going to be putting out a certain quality of light. After you've used it for 500 hours, that quality of light has changed. It's not perceptible to your eyes, but if you had instruments that could actually measure that, you could tell that there were differences that were occurring. And then one day, you're going to turn on the light bulb and it's going to go pop and it's going to blow out and it's time to replace the light. And that's what sensor deterioration is. And when you're heating up a hot wire, you're changing it every time you heat it up and cool it down, just like you're doing in the incandescent light bulbs. And there will come a point where the wire will break and you'll have to replace it. But before that happens, every time you use it, it's going to be slightly different. And in the case of monitoring gases and vapors, it actually does matter, because that you're going to have to calibrate very, very sensitive differences. And so calibration is real important. You have to calibrate these each and every time you use them, because the sensors are changing over time. It's kind of like a moving target, because that wire is going to be changing, just like the light bulbs will in your house. And one day they'll actually deteriorate to the point they can't be used anymore. But this is what a Wheatstone bridge looks like. You have a compensatory filament over here, which is going to be balancing out the detector filament over here. And the detector filament is going to be pushing in or pulling in combustible gases over this wire. And if they're combustible and in the right range, they're going to burn. And if they burn, this wire is going to heat up. And if this wire heats up, the resistance in the circuit is going to change, and you can measure that. And therefore, you can correlate that with the concentration of the combustible gas that you pulled in your filament. It's a pretty simple system. That's why it's one of the oldest for combustible gases, but it was used early in the mining industry. If there are a lot of methane present or something that could blow up, you would use these things to determine what the concentration of the gas was, and if you're in the explosive range for that. Now, they are going to have to be calibrated every time, as I mentioned earlier, and this is just a calibration curve that can be used for calibrating them. Usually you'll get standards with them. The other thing about using a combustible gas meter is, just like anything that you burn, you've got to make sure that it's not too rich or too lean. And so there's an optimum concentration for it to burn. If you don't have sufficient gas present, it's not going to burn. And that's below the lower explosive limit, so you cannot burn this gas. Alternatively, if it's too rich and there's not adequate oxygen present for as part of the burning process, you can't burn it either. So there's a range where the gas is going to burn within the chamber. And again, you've got to have an adequate concentration for it to ignite. If it's too lean, it won't ignite. It's just kind of like how your cars work. They have to be, the fuel mixture has to be just right with oxygen. If it's too lean, it's not going to burn. If it's too rich, it's not going to burn. And so there's a range that they will be able to pick up the concentrations of gases and vapors. And you just need to know what the range is for the specific gas. But again, if it's 100% environment of the gas, it's not going to burn. And if it's 0.0001%, there's not enough of it to burn. There's too much oxygen. So it's got to be in this explosive range for it to work adequately. This is an example of one. This is a Krokow gas and vapor, combustible gas meter. They're handheld, and they have the lower. You can see here it reads out in percent, and it can give you what the range of your combustible gas is going to be. Now the next is a solid state sensor, and a solid state sensor works kind of like electrochemical sensors, except instead of having an electrochemical present, you've a liquid. You have it present as some kind of a coating on a sensor material. These are used a lot as alarm systems because you can put these, if you have a hydrogen sulfide tank or something like that you're worried about a leak, you can put a sensor on the wall and it'll be stable for quite a long time, and you can tie in that stable with an alarm system, so if the concentration hits 5 parts per million or something, you'll have an alarm go off and have a warning system. But the way that they work is that the chemical will come into contact with the sensor, and the sensor is going to be specific for detecting that particular type of material, and it'll cause a chemical reaction. And when a chemical reaction occurs, you're going to have a change in this current. And when that change in current occurs, you can trip it to an alarm system. And so these are very good for measuring low concentrations of certain type of contaminants, particularly in remote areas where you may have a leak occurring. And a little bit more about them. They're also called metal oxide semiconductor sensors. They're, again, solid state. They can detect a lot of different compounds. They're small. They don't cost much. They're very easy. You do have some specificity issues. Sometimes they can not have adequate sensitivity, and their stability varies depending upon the environment. Sometimes they can be very, very stable, but you may have some water issues or something like that can cause a problem. This is a link to one, a solid-state sensor, and an application of where you're typically going to find them. This is SBG200 wall-mounted gas monitor. It's an affordable, solid-state, completely contained, self-contained monitor capable of detecting a variety of toxic and flammable gases and vapors. Has several different sensors available, well below their explosive limit or the OSHA ceiling. And this tells you a little bit about them, but this one plugs into a 110-volt outlet. And you can monitor it by something. You can set up alarm systems like light or sound systems. It could either have a flashing light or a siren that goes off. have a backup battery system, etc. So it can give you a lot of information, especially if there's a leak. And these are some common gases and things that will be set at. Benzene, you can set it at 2 to 750 part per million. Ammonia, 50 part per million. Hydrogen sulfide, 10 to 20 part per million. So if you have a leak of hydrogen sulfide coming out, you can pick that up. But these solid-state sensors are really good for an alarm type of a situation. Now, the next one of these photoionization detectors are the ones that I am completely amazed by. These are general survey instruments that did not exist when I was in grad school. When I was in grad school, I did a lot of work with UV light on measuring different enzymatic reactions in a laboratory. And to do that, I had a UV light that was about the size of that overhead projector over there with the UV lamp. And I would have to plug it in. If I was going to do experiments in the morning, I'd have to plug it in at 8 o'clock, and I wouldn't be able to use it until 9 o'clock. It took about an hour for the light to stabilize before I could get meaningful readings off of it. And it was an expensive piece of instrumentation, but it was pretty common for measuring a lot of different types of enzymatic reactions. Subsequent to that, this UV light has been adapted to other types of technologies and measuring things like I used to do, but a lot of work in microprocessing that's been applied to what you see from having a huge computer down to a computer that you can fit in your pants pocket is absolutely incredible. And there have been the same type of changings with the applications of UV light as well. And I'll tell you a little bit more about that in just a second. But they work by the fact that UV light has the potential to create ion pairs. After the next test, we're going to get into ionizing radiation. And the difference between ionizing radiation and non-ionizing radiation is that ionizing radiation can produce ion pairs. Non-ionizing radiation, like FM radio waves and things like that, has energy and it's radiation, but it can't produce ion pairs. As you progress up the electromagnetic spectrum and get into shorter and shorter wavelengths with higher and higher energy, you hit a point where you can start having sufficient energy to break something apart and create an ion pair, i.e. a plus charge and a minus charge. And when you get into the X-ray range, you're clearly in that area. But before you get to the X-ray range, you go through your visible light range, and then you get into your ultraviolet light range. And somewhere in the ultraviolet light range, you get a portion of the ultraviolet spectrum where you have enough energy to create ion pairs. And that's what gives you sunburn if you go outside a lot, or you can use that technology to create ion pairs and measure different types of gases and vapors, because what you're measuring is ion pairs. Because every gas and vapor has what's called an ionization potential. And that's how much energy you have to hit it with to make it into a plus charge and a minus charge. And if you can do that, you can measure it. So that's kind of the technology that it's based on. And this is a list of a lot of different common chemicals. Like benzene has an ionization potential in electron volts of 9.25. And what that means is if you hit benzene with 9.25 electron volts of energy, you can create an ion pair. So you have a plus charge and a minus charge, and you can measure that. If you hit it with 8.25, nothing's going to happen. You have to hit it with at least the amount of energy and the ionization potential. And this is a chart of ionization potential for common chemicals. Thioline's 8.82, pentane's 10.35, hydrogen sulfide's 10.46, cyanide is hydrogen cyanide's 13.91. And as long as you hit these chemicals with sufficient energy to be at a minimum of their ionization potential, you can create ion pairs. Hit it below that, you're not going to create ion pairs. So you've got to hit it with at least that much energy, and then you can measure it. And what is an ion pair? An R is an organic group like benzene or any chemical that was on the previous page. HV is a representation of UV light. You hit the chemical with UV light of sufficient energy to create ion pairs. This is your ion pair. You've got a plus charge and it kicks off an electron. That's your minus charge. And when we never have a charge, you can measure it, just like we could with our electrochemical sensors and things like that earlier. If you can make something charged, it's much easier to measure by having charges go to different sides and having a concentration gradient. So that's what these things are doing with photoionization detection. is using UV light to create ion pairs and therefore measure ion pairs. This is an example of a photoionization detector. This is a PID, stands for photoionization detector. This is a Mini-Ray 3000. This is a handheld model. Ray System makes these. Jeff Steen runs the Region 1 hazmat team that has certain equipment to go out and try to detect spills and leaks and potential bioterrorism or terrorism attacks. And they have several of these Ray System photoionization detectors on in their equipment inventory. They cost between $5,000 and $10,000 a piece. They're pretty expensive. But you can go to Ray System's site. And it gives you a little bit more description of their Mini-Ray 3000, as well as a lot of their other photoionization detection systems that are available out there. So that's the Mini-Ray 3000 and a little bit on Ray Systems. The next kind is a flame ionization detector. And similar to a photoionization detector, they use energy, but instead of UV light, they use flames to produce ions. And most organic vapors can be burned, so they can produce ions with this technology. And it's useful for a lot of different sampling, including atmospheric sampling, because this technology has low sensitivity to water, oxygen, and nitrogen, so you're not going to get interference with common atmospheric sampling contaminants or constituents. And this is kind of how they work. You'll take the gas and vapor and you'll put it on a flame and burn it. That's what the flame ionization is. And you'll create ions, and the ions can be collected at the collector electrodes, create a gradient, and measure that. And so it's similar to how you measure the ions that are produced from photoionization detectors. A lot of gases and vapors are used for these. Benzene, I'm just listing a few of these. Ethane, hexane, phenol, toluene, vinyl chloride. You can use a flame ionization detector to monitor. This is an example of one from Microfid, Photovac flame ionization detector. This will detect VOCs, or volatile organic compounds. And again, they're useful for atmospheric sampling, so they can be used for a lot of the EPA message if you're at Superfund sites for things like that. And you can use these to detect. I'll just read this a little bit. EPA Method 21, compliant fugitive emission monitoring, detects 0.1 to 5,000 part per million volatile organic compounds. So these are a pretty simple handheld instrumentation, but they rely on a flame inside to ionize the gas or vapor. Then you can have gases and vapors that monitor multiple gases and vapors, and this includes IR gas analyzers, portable gas chromatographs, and detector tubes. And I want to go through these a little bit and tell you somewhat how these work. Many of you in organic chemistry have had an opportunity to do infrared analysis. And infrared light is on the near region of the visible spectrum. You go infrared, visible, ultraviolet. So it has less energy than does a visible light. And infrared is useful in a lot of technologies. For example, when I was home on Sunday not feeling so good and I was wanting to watch different movies and sports on TV, lacrosse actually was on Sunday afternoon, which I was really excited about because I used to play that. I want to switch channels and go from different things. I do that using infrared technology. My little remote control has an infrared sensor in it that talks to the TV or the stereo that switches back and forth. So I have an infrared light beam that I can't see because it's below the visible light range that'll point it at it, press a button, and it'll change the channel, which to this day I think is an amazing technology because the way you can go through so many channels. But some chemicals and substances will absorb infrared light, and these are lists of things like alkenes and alkynes and aromatic aldehydes, ketones. So they all absorb infrared light in characteristic spectrum, and you can measure that. And some things don't absorb infrared light. They can block it completely, like my dogs. My dogs are standing between me and the TV. I have to physically move the dog sometimes so that I can change the channel because they absorb 100% ultraviolet light. But other chemicals will just absorb partially of it. And for organic chemistry, you can use this as a very good identification with an infrared spectrum for seeing where absorption bands are. And if you have an absorption band at a 5.6 to 5.9, that's indicative of a ketone. If you see one at 3.25 to 3.45, you've got an alkene present. And I know when I took organic chemistry years ago, that we used to have an unknown analysis where we get spectra from different types of instrumentation, including infrared spectra, to try to piece together what our unknown compound was. And I don't know if you still do that or not in organic, but this technology can be used very sensitively to measure different types of gases and vapors, provided that they have the ability to absorb infrared light. And this is an example of an infrared spectrum. This happens to be for sulfur hexafluoride. You can see it has specific bands, and these bands are going to give you a qualitative analysis of what the gas and vapor is, and you can quantitate that to determine a little bit more sophisticated what the levels are. The advantage of this is that you can use this to simultaneously determine more than one gas or vapor. And this is an example of an instrument that can do that. This is a portable infrared analyzer. This is a Moran Sapphire analyzer. And you can go into an environment where you have multiple alkenes, alkanes, alkynes, and simultaneously analyze those to determine what the concentrations of the gases and vapors are. I'll just read the little description on this. This is a Moran portable IR analyzer. Wavelength coverage permits outstanding single and multi-gas monitoring as well as unknown compound identification, making the Moran Sapphire the most reliable gas detection system on the market today. And there are certain advantages to doing this. It can pick up a wide range of different chemicals. It says here 100, 150. But if you go into an area where you know you have multiple different gases exposures that are common solvents and can absorb ultraviolet light, you can monitor for many of these simultaneously. Or if there's one that you're not sure what it is, you do have unique identification based upon absorption. So there are a lot of applications for this particular type of instrumentation. When I was at Arkansas, we had a lot of students that worked in their Department of Occupational Safety and Health, and this is about the only direct reading instrument that they had in their inventory, because when they looked at all the ones that are on the market, this was the most applicable to a hospital setting, because a lot of hospitals will use different types of organic compounds for disinfectants and sterilants and things like that, and they all have infrared absorption bands. So you could pick up a lot of different chemicals with this. It was a really useful probe in that type of environment, as well as many others. The next is a gas chromatograph. And gas chromatography is a very common laboratory analysis technique. If you do drug testing, there's been a lot in the newspaper recently about performance-enhancing drugs. What you do to measure those is you typically try to isolate them and then take the isolated compound and put it into some kind of a detector and determine it from that. The example that I talked about in class the other day for determining the advantages of the detection of heptachlorochlordane and DDT was used by what I said was the GC ECD. What that meant was when I sent the samples to the laboratory, and this is really common with drug testing and most organic solvents and things like that, you'll send them to the laboratory and they'll run them through a gas chromatography setup, and this is what a GC is. And then they'll have a detector. The detector in that particular paper was an electron capture detector. You can use all kinds of detectors. You can use a photoionization detector, a flame ionization detector, an ultraviolet light. You can use mass spectroscopy, which is what's commonly used in performance-enhancing drugs. So you can use a lot of different detection systems. But the way that they work is you'll take a complex mixture, your sample, and what you want to do is try to isolate your compound of interest. And you do that by putting it down a column. How many of you have ever run a race before? A 5K, a 10K, a marathon, something like that? A couple of you have. What happens at a race is everybody's at the starting line at the same time. But then you go to the finish line, and you're going to see people straggling in at all kinds of different times. You don't see the same pack that was at the starting line cross together at the finish line. Wouldn't be a race otherwise. And that's kind of what these gas chromatography columns do. You start with it's like a 5K race where you've got 200 people, and they're all here at the very beginning of the start line, and they're all pumped up and ready to go, and then they say go. And what's going to happen pretty quickly is you're going to have a separation. Some people are faster than others. And the faster ones are going to come out of the column first, and the slower ones are going to come out of the column last. So what you do with a gas chromatography column is you set it up to have different types of packing material. You could have really small beads in there, for example. And so a large compound is not going to go in and out of the beads. It's going to go on the sides and just go down and come out fast. So you could separate things by size using this technology. Or you could separate them by charge if you have charge compounds. But let's go back to sides. If you're in the petroleum industry and you've got a lot of alkanes present, like pentane, octane, heptane, whatever, and you want to separate those out, you can separate them by size. So you can put beads in here so that the larger ones can't go back and forth and in and out of the beads and beads slowed down. They're going to go out the column quicker, and the smaller the chemical is, it's going to come out slower. So at the end of the column, everything that's alike is going to come out together. So if it's all octanes, they're all going to come out at the same time. Pentanes are all going to come out at the same time. Heptanes are all going to come out at the same time. So you can separate out by size using this type of technology as one measure. You can put in all different kinds of packing material to separate out by however you want to. But what it will do is it will separate out a complex mixture of chemicals, and then you can measure each chemical separately with the detector. So when the alkanes come out, you'll know that. You can just measure the octane constituent at a particular point in time. This is used a lot for identification of complex mixtures as well. I remember I didn't graduate from, but I went to the University of Tennessee for a year as took analytical chemistry courses before I switched to toxicology. And I remember having to read a lot of analytical articles during that time period. And I was reading one about canine pheromone identification, which struck me to this day because I'm a dog lover. But they had a picture in there and how they were doing this. What they're trying to do is determine what pheromones were chemically. And it's a complex chemical. You wanted to know what the stereoisomeric positions were on the molecule. But they had to isolate and identify it, first of all, to do this. And basically, if you have a dog, if you have a male dog, and I've got two male dogs and a female dog. They're all spayed, but if you have a male dog and there is a female dog in Heaton, Callaway County, my dogs know it. And they can pick up one or two molecules of a pheromone from a female dog. And it's a pretty noticeable reaction when the dogs know that the female dog is in heat. And so a male dog is an extremely sensitive detector of the pheromone for a female dog. And that's what this paper was about. It was trying to identify what is the chemical that goes out in the air from a female dog that attracts male dogs. And they didn't know what it was, so the first thing they had to do was isolate it. So they would collect samples from female dogs in heat, basically a gooey mess, and they would inject it into a GC. And they had a picture of this in the journal article with the GC there, and the detector, instead of having a detector in this, like in this picture, it had a male dog. So they had a male dog sitting there with this thing on its nose, and as chemicals were coming down the column, they wanted to find out, where's the chemical isolated that the dog is the pheromone. So the dog would sit there and, it'd just be sitting there. And all of a sudden when that pheromone hits it, kaboom, and it's, that dog has determine that the pheromone's present, and then you can say, okay, that came off the column at 18 minutes and 57 seconds. And so the next batch you would run through, you would start collecting the sample that came off at 18 minutes and 50 seconds until you had a sufficient quantity of it that you could then run it on a gas chromatography and other identification procedures. And that way you can determine what the big molecule is and, you know, all the different stereo constituents that made this pheromone potent to a male dog. And so this technique is used in a lot of different applications, and that's just one that I remember because that was the first time I'd read a GC paper, had a dog as a detector, and I thought that was kind of neat. But you can use any detector you want to for this technology, but it's really good because it can separate out a complex mixture. So if you go into an area where there's a lot of stuff present and you're not interested in everything, you just want to know what this one chemical is, it can isolate that for you and you can detect it. This is an example of how that's useful. This is a portable gas field chromatograph, a Petropro portable GC. Those of you that have done internships in the petroleum industry may have even had an opportunity to use one of these before. They measure the BTEX, which is an acronym for benzene, toluene, ethylbenzene, and xylene. They can measure these at part per billion levels, so these are pretty sensitive, and it's a small handheld instrument. This one happens to be by Photovac. Call for pricing. You'll see that's again with a lot of instrumentation, but it'll tell you for certain chemicals in the petroleum industry like benzene. Now this isn't real time; it does have to travel down the column before you can get a reading, but you don't have to wait that long. You can get a benzene analysis in 60 seconds. You can get your entire BTEX analysis in less than three minutes. That whole GC components that I showed you on the previous slide. They've miniaturized them so it can fit in this case. It only weighs 15 pounds, so that's light enough that you can lug it around a different facility and get BTEX measurements. And it's pretty easy to use. And so you can use these for many different type of applications, but you do have a GC column that's inside of these, which are separating out the chemicals by the process here of having them go down a column, come out at different times, and then measuring them. Now, the last one of these direct reading instruments is kind of a quick and dirty analysis called Draeger tubes. And you can get these. I have 350 gases and vapors. It could be even more than that, depending on how many are on the vendor side. You can get single readings or multiple readings on these. You can have it has a bellows here, which basically you open up and put air in and pull air through this particular tube. You break off the end of the tubes first. You stick it on the bellows, and you'll pull air through the tube. And within the tube, you have a chemical reactant, and it's going to react with different types of chemicals you want to measure with a colorimetric change. So if you're concerned about ammonia, you'll get an ammonia tube, and it'll be a certain color, and ammonia will change it to a different color. And you can watch that and look at it. And there are some trade-offs with these. They're not extremely accurate, but one area where they're applicable is, as I talked about on Thursday for exposure evaluation, you want to walk through different areas and determine, do I have a problem or not for air sampling? And these can give you kind of a quick and dirty qualitative analysis. If you've got a positive result over a certain level, I can tell you, I probably have to do some more sampling here. But if your Draeger tubes are showing up empty, that may not be an area you need to focus on. So they can give you a really good qualitative analysis in real time, because you can look at it and see whether or not that tube changed color. And you can get these for a lot of different gases and vapors, and they're pretty inexpensive. A whole lot less than the $250 a pop I was showing you for sending off things to a laboratory. And this is just a description of colorimetric tubes and some of the Draeger tubes that are available from this particular website, where you can go and use these different types of Draeger tubes. There's a lot of them present. And again, you can get bellows to hold multiple tubes at once, so you can look at more than just one at a time. But they're very useful, but there's some trade-offs with them. Again, they're better for a qualitative analysis rather than a quantitative analysis. And the last part that I wanted to talk about is on aerosol sampling and how that will work with a direct reading, but I think I'll put that off until Thursday and pick that up at this point.